Hi everyone. Today I'm going to present this paper by Borjon, which was published in 2016. It's called "What Mechanism Drives," and no, it's not called that. It's called "Arousal Dynamics Drive Vocal Production in Marmoset Monkeys," and they basically look at what mechanism drives an individual primate to produce a vocalization at all. So they investigated here the role of arousal during naturally occurring vocal production in marmoset monkeys. And they used different techniques to examine this role. And I wanted to discuss together about these techniques that they use. So they basically investigated the arousal dynamics related to the spontaneous vocal production. And they say that they exploited the fact that this species readily produce a single type of contact call, which is the phi call. And it happens during social isolation as well. And in marmoset monkeys, this call is produced with some regularity, once every 10 seconds or so, without the need of an external sensory trigger, such as the presence of another marmoset monkey. Here you can hear some examples of this phi call that I just mentioned. I think that's enough for today. Oh yeah, okay. So here is a detailed explanation for how they gathered the phi vocalizations from data, which consist of four monkeys. Is that
Sure,
okay?
can I ask you a question? Oh, sorry, I interrupted you.
No worries, you can go.
Is it the case, sorry if I missed this, is it the case that they produce phi calls with other marmosets, but then if they're left by themselves, they produce one every 10 seconds spontaneously?
Yeah, it's actually regardless. So it's in both circumstances they have this phi call, which is observed to happen reflexively without necessarily requiring an external stimulus.
Okay. But do they use it? Oh, actually, I'll just let you explain because probably that's the answer to this question.
Okay. Um,
Sorry.
no worries. If you have more questions, you can ask. So here's a detailed explanation for how they gathered these V vocalizations from data. So they band passed the entire recorded signal between 5 and 8 kilohertz for each session. And the reason why they chose this interval is because this is the known fundamental frequency of phi calls in these monkeys. So their frequency band while vocalizing is between 5 to 8 kilohertz. And then they compared the amplitude of the signal at this frequency band for the periods with and without call. And they decide, so this was basically their decision process about how they should define a phi call within which interval, I mean. And they decided that the onset and offset gaps longer than 1 second indicated separate calls, whereas gaps shorter than or equal to 1 indicated syllables from the same call. So based on these calculations, they produced a total of 427 calls across a span of 26 sessions.
But they didn't differentiate between syllables.
No, no.
No, so it's just part of the same call.
Yeah, yeah. And I wanted to briefly go over some technical details on how they prepared for the heart rate data for the analysis, assuming that it's the Methods Club journal. So yeah, I'll be boring a little bit, bear with me. So here in the text, they say that they downsampled the data from 40 kilohertz to 1500 hertz to extract the cardiac lines. So what does it mean? So the heart signal was originally recorded at very high resolution, which was 40,000 samples per second, and then they reduced it to 1500 samples per second because the heart rate signal doesn't change that fast, and this helps them make the analysis easier. So that's how they convert the data into a manageable size. And then in the paper, they say that these signals were then high-pass filtered at 15 hertz to preserve the rapid waveform of the heartbeat. What does it mean? So they use the high-pass filter to keep only the faster changing parts of the signal, which include sharp spikes created by heartbeats. Anything slower was filtered out because they wanted to look at those spikes in particular. And then I want to, yeah, okay. So, and then to remove line noise, the resulting signal was notch filtered at 60 hertz. What does it mean? So they say that electrical systems can introduce a hum, a line noise at 60 hertz. So they applied a notch filter to remove this specific frequency from recording. So it's like cleaning up the noise. And then they say the heartbeats were detected using an adaptive threshold of 1 second duration to find cardiac spikes greater than 95th percentile of the amplitude at each second of the signal. So this is an automatic method that they use to detect heartbeats based on their amplitude size. And they looked at each second of the recording and marked any large spike in that second above top 5%. So that's how they detected the heartbeats. And
Oh, sorry.
go ahead.
This seems it's a little bit weird that they wrote their own heart rate detection algorithm because there's tons of really good ones out there. I don't know, this isn't really a question or anything, but it just seems a little bit odd.
I mean, I was also I found it interesting that they provided so much detail as well, but I'm happy about it. So
Wasn't this paper from 10 years ago or 8 years ago?
2016.
Yeah, so maybe it's, the reason was like, they have them now, but did they have that information 10 years ago? Or like detecting heartbeats? I don't know, because I wasn't doing research then.
Yeah,
I mean,
I always write my own. I just like to know what it's doing. I prefer to do. It's quite easy. It's just like I just prefer to know what it's doing. Yeah.
Should I skip the slides? Did I get it right? No? Should I?
no, you
No,
did.
I mean, it's fine. I didn't really spend ages on this, but yeah. So it looks good, yeah.
Okay, and to calculate the heart rate, they constructed a binary series of heart rate counts and convolved the resulting series into 1 second Gaussian window. So they did this to smooth the data out and so that they have an on and off series showing exactly when heartbeats occurred. And here's how they prepared for the respiratory data analysis. So they compared the link between respiration and heart rate during the onset of Phi calls. And they applied a similar noise control procedure to determine the best channel of cardiac activity. And so segments of signals that didn't demonstrate as respiratory signal were excluded from analysis. And they were interested in physiological signals related to respiration, so they downsampled the data. Similar logic applied to the respiration again. So the original signal was recorded at 40,000 samples per second, which was way too detailed for slow signals like breathing, and they reduced it to 50 samples per second. So it would be easier to track breathing patterns. And because the researchers were working with marmosets, then 3 hertz reflects an upper end of their rapid breathing rate. So they match it to their breathing rate, which is known already, which is 3 hertz. So yeah. And finally, they removed the DC offset, and then they high pass filtered the signal at 1 hertz. And and then a low pass filtered at 4 hertz. So they looked at the interval between 1 and 4 hertz, basically. Yeah, to clean the signal. And so here they explain why they link breathing to vocalizations. And they say because mammals, including primates, produce vocalizations using expiration-driven vocal fold movements, they wanted to make sure that the respiratory signal always had a consistent phase relationship with vocal output. What does it mean? So basically, animals make sounds when they breathe out. So the researchers wanted to make sure that breathing signal matched correctly in time with when sounds were produced. So because it's an already known phenomenon, which is the fact that expiration phase is related to making sounds, they compared the call onset and call offset peaks, and they wanted to make sure that it goes down as expiration starts or continues, which is the negative slope you see on the red line over there.
But this isn't just those types of noises, is it? Because they're sustained, yeah?
Mm-hmm.
They're going to be going, then that's changing the rate at which they're breathing, right?
Mm-hmm.
Because to be going, like that, you're letting your breath out slowly, right?
Mm-hmm.
So we didn't really talk about that in the context of this other paper, that 2003, but has anyone who's read that paper closely? So yeah, we should talk about that. But also I think we could do with a bit of big picture stuff, Ishil. We've kind of jumped straight into the weeds. For those of you who knew, we could do with a bit of a big picture stuff about why we're interested in this type of work. But should we do the fine grain picture first and then the big picture, just a quick big picture?
I have the big picture towards the...
Oh, the big picture's coming. Okay, fine, okay. For the small picture,
I can go to the big picture, and if you want more...
No. If you, however you want to do it, that's fine.
Okay.
The small picture is, it is not just a question of just there's a sine wave going on, which is the breathing, because the talking alters your breathing patterns, right?
Yeah, there's different phases of breathing that is associated with the vocalization onset.
Mm-hmm.
Okay, so and here they used a mathematical method which is called the Hilbert transform to figure out the exact phase of the breathing cycle at every moment. In this analysis, whenever the Hilbert angle hit 0, it marked the start of breathing out. So these time points were used to figure out how fast the subject was breathing, and they made a simple timeline where the exact start of expiration was marked with a 1 and everything else was 0, which is the middle one you see, the binary one. And then they applied a 2-second smoothing curve to turn these points into a smooth graph of breathing over time, which is the bottom graph. So they say this method is commonly used in neuroscience to track how often brain spikes, etc. happen. And
It doesn't work with humans. I've tried this with humans. It doesn't work at all neatly.
Doesn't work?
But you put a little belt around. I can't remember what you said when their raw data was, but I tried it once. We've got one sitting in this. We've got a couple sitting somewhere in the lab. You just put a belt round and it's got a little pressure sensor there, and the times when it's going in and times when it's going out. And then you get a line that looks like that for just the diameter of the rib cage.
Mm-hmm.
And you can do the same. You can look at the inflection points at the time when they're breathing in and out, but it doesn't work. It's not. There's two, because if you twist or you move, then that also changes the size of your rib cage. So we just didn't manage. So we ended up just thinking it was junk data and chucking it out.
I wonder how they like control it with animals, because maybe they apply more control over animals, probably, I'm guessing.
Maybe, yeah.
So they were trying to see if there's a pattern between how fast the heart is beating and when a vocalization occurs. Not just one, but across the whole recording session. So they broke the recording into 1-second chunks and calculated the average heart rate in each chunk. So they created a timeline. And because each marmoset has a different natural heart rate, they converted the heart rate values into percentiles. And for each 1 second heart rate bin, they asked how much time passes until next vocal call. So here, instead of asking how long until the next call, they now asked what's the chance that a call will happen soon, given the current heart rate. So for that, they chose a 23-second window because that was, on average, the shortest time between a given heart rate level and the call. So they looked at this question: is there a call within 23 seconds of this heart rate? Instead of using it every 1% step, they group data into chunks of 5%, but that's too much detail, I think. So these percentiles stand for the magnitude of the heart rate. So there's like an inverse relationship between time from vocal onset and magnitude of the heart rate, you can see in this graph. Yeah, and they next examined the dynamics of the heart rate during the moments preceding and following the production of a call. So these vocalizations are known to differ in their durations, and they therefore plotted the heart rate aligned to vocalization onset and offset separately. So these red lines indicate epochs that were significantly different from baseline cardiac activity, if you look at the graph A, upper graph. So we can see here, and also the light green vertical shaded area is the onset and offset of a call. So here we can see that marmosets showed an increase in heart rate before vocal production, followed by a rapid heart rate deceleration if you look at the area, the shaded area. So the heart rate increase began slowly, starting roughly 23 seconds before the onset of a vocalization. At vocal offset, the steep deceleration you can see. Yeah, and yeah, that's pretty much.
And the deceleration
Sorry.
and the deceleration is because you've been holding your breath, right?
Yeah, same.
So it's a reaction to the fact that you've been holding your breath because you don't breathe in and out so much when you're vocalizing. But Gio, these look very different to your graphs looking at, sorry, for those of you who don't know, we're just doing a paper at the moment. Initial's writing a graph, which you're going to get to, Ishil, looking at the same thing in infants. So is this, how does stress kind of relate to the dynamics of vocal production in infants? But Gio, your plots look very different. There's nothing 20 seconds before, is there?
What do you mean nothing?
Well, there's no increases in heart rate 20 seconds before vocalization. Or I can't remember.
Oh no, it's like very centered on the vocal onset.
Yeah.
The peak heart rate.
And when does it start to go? When's it first above chance?
Well, we're taking a much bigger view when on those plots that go back like 10 minutes before.
Oh, okay. So that's why I was doing different. Oh, I'd forgotten. Okay, fine. So it's quite similar, the time course of the arousal changes then, that we're finding compared to what these guys found with monkeys. Marmosets.
Yeah, but they don't dip. Like I don't see the dip.
Yeah, we don't see the dip after, but I was thinking that's just because did they say how long the average vocalization was? But from that tape, they were quite long, the vocalizations, yeah.
Yeah, durations, you mean?
Yeah.
2 seconds, 2.2 seconds to 1 second. That's what I'm seeing here. Ranging from 2 to 1 second, yeah.
What, the duration of the vocalizations?
Yeah.
Why are you seeing that from the width of the average call duration? I suppose average call duration, yeah.
That's the green shaded area.
Yeah, I see. Sorry, it's
the X distance. Yeah. Yeah. So sorry?
I was saying that it's weird then that it does look so different, because Gio's right. We don't see a deceleration straight after they've been vocalizing.
Am I being dumb here? But doesn't this look exactly like you would expect with RSA, like as in lung volume increases. Nobody knows exactly why, but it's probably something to do with pressure on the heart. Heart rate increases, then the lungs empty rapidly due to it being a fecal. Pressure on the heart is relieved, heart rate drops. Like I get this is different from a regular respiration, but also you could expect that fecals have some special characteristics that might like accentuate the effect. But surely we would expect this.
Yeah, that's what I was saying. If you hold your breath, your heart rate goes down.
Well, it's not just holding the breath though, it's like with lung filling. So lung filling your lungs causes your heart rate to rise, and emptying them causes it to drop.
Okay.
Yeah.
And there's like a range of theories about why this happens, but probably it's something to do with like cardiac output being limited by the fact that the lungs are inflated.
Interesting.
There is a comment in the discussion, and they kind of like interpret this trend as a way of self-soothing. Like during expiration, you make a sound, and your heart rate decelerates. So it's they frame it as as a form of self-soothing. Yeah. Okay, I'll continue. So, and then they discuss about some like physiological phenomena, which is called the Barrow reflex, and they say that the physiology of mammals, in this physiology, there's this rhythmic oscillation at the core of this physiology, and this rhythmic oscillation is based on this Barrow reflex, and this is basically it's an inherent fast-acting negative feedback loop that we have. And for instance, in the veins there are sensors, and this is just an example. And if the blood pressure rises, these baroreceptors, these sensors, stretch, and a signal is sent to the brainstem. Yeah, somewhere in the brainstem, and this brainstem adjusts this automatic output. And basically, the reason why it's called a negative feedback loop is because it's acting the negative way towards a homeostatic trend, which means like if your heart rate increases, the brainstem is notified, and it's kind of creates an action to lower it, so to bring the state to a optimal level. So there's this circular loop, which is stemming from this rhythmic oscillation inherent in the Barrow reflex. And it helps the mechanism to stabilize itself without being overactive. And then they say at the core of this rhythmic oscillation, there is a certain trend of wave, which they call the Mayer wave, and they call it the oscillatory signature of the autonomic nervous system, which is present in both cardiac and respiratory measures, and it represents perturbations to the Barrow reflex. So yeah, I just explained that to you. For instance, this is just a simple graph, which has the heart rate at the upper, the gray one, which we have. This is just a regular heart rate. And at the bottom, the blue one is a Mayer wave. It is basically achieved through low band passing the existing heart rate. And if you bring it to a lower frequency, you get this all the time, they say. You get this trend, this oscillation, which is what can I say, in an absolute like oscillation trend. Yeah, and they say this vocal behavior is also entrained to, shaped by this internal physiological rhythm, and they say it's not random. Yeah, so, and that's what they wanted to construct here. They construct, so in humans, I think these waves occur at 0.1 hertz, and they apply the bandpass filter to the monkey heart rate rhythm as well. And they say it's not like an imaginary thing, it's a real rhythmic output that they have, because I always thought of it as, when I was first reading it, I kind of assumed it as a, like, you know, through bootstrapping we create some control data. So that's how my brain, like, I thought it was something like that, but they really suggest that it's a real oscillation that is inherent in the physiology. And yeah, most mammals exhibit a range of 0.04 to 0.15 hertz, and they observed a 0.145 hertz frequency of vocal production across these monkeys. Yeah. What do they do with this? I'll explain. So this oscillation is through like an up and down, like a sine wave, like basically. And there are peak points which they define at the angle 0, and there are some throw points around 180. So it's a cycle basically. And so what does it have to do with respiration and heart rate? So they calculated this heart rate and respiration relative to the onset of phenols. So they noticed that these vocalization and respiratory rate around the phenols show a similar Mayer wave trend, which goes up and down, but the timing is different depending on which physiological mechanism we're talking about. So for instance, if you look at the upper graph, C, so for heart rate, vocal onset occurs in the descending phase. Okay, this was not so easy to figure it out, but I think, how can I explain it better? If you look at the lower image, and if you look at the blue one on the left, that's for the heart rate. And where the place where I put the arrow, just above 0, is where the vocalization onset takes place. So they say it is in the descending phase of the heart rate when vocal onset appears. But the tricky thing is, if you are talking about the descending phase, then it should be somewhere between 180 to 0 if at the very bottom of the sine wave, if you're looking at it. So I think there's a mistake that they did there, because look, if we are talking about the peak, it should be 0 at the top, but in the second one, the 180 is at the top, which doesn't make sense. I think this is a mistake, but maybe what do you think? Any comments on that? Because I spent so many minutes trying to figure this out, and I figured it out that in a different paper, they put this actually, lower right one. But
If you go back to the page before, right there where, nope, right there, nope, there. The phase and the angle, the trough is the bottom one and the peak is 0. So that matches the 0 being at the top and the 180 being at the bottom.
but
So
if you look at
the upper
falling and
right-hand side.
rising, if you look at falling and rising, it doesn't
With
make
the-
sense.
Yeah, so where's it?
0 to
drop.
90, 0 to 180, it should be increasing, but it's the opposite. So anyhow, yeah, I think there's a mistake there, because they do the exact opposite in a different paper that they published, like naming the angles, I mean.
So what do they look at these independent of the other ones? Yeah, because obviously if I'm holding my breath when I'm breathing, sorry, I'm holding my breath when I'm talking, yeah, that will then drive a decrease in my heart rate. But what's causing what? Is it talking causing me to slow down my respiration rate? versus the talking causing my heart rate to slow down, you know, because you've got lots of things that are all interdependent. Yeah.
Yeah, I didn't get the impression or interpretation that they did anything to control for either one of these, respiratory or heart rate, while looking at the other one. But in the upcoming slides, they made a covariance matrix. They defined it as a compound unit of respiration and heart rate together. So, and I don't think so. They didn't really control for either one of them.
Okay.
So this is another paper. I'll very briefly discuss this paper because they use a similar analysis. They're this time looking at vocalizations of 24-month-old infants, humans, and they predicted that changes in heart rate are dynamic, and the point in phase along increasing and decreasing heart rate may be more relevant to vocal production than its percentile value. So where the heart rate is within the phase change is more important than just pointing 1 percentile value, they say. And ongoing heart rate percentiles were therefore converted into phase angles with 0 degree corresponding to the local peak, which was the opposite of in the paper which I just showed you, and 180 degrees corresponding to the local throw. And so they found that vocalizations produced at the peak were longer than expected by chance. So functionally, vocalizations produced just before the throw, while heart rate is decelerating, were more likely to be recognized as well. So they look at different things. They look at what point of the heart rate change does the vocalization start, and they also look at which points of the heart rate are vocalizations longer or shorter, B. And for C, they asked naive listeners to determine whether the sounds that these babies make are recognizable or not at a varying levels. Not so recognizable, very recognizable, not recognizable at all, etc. So yeah, they defined the red ones are the phases in which these measures are more saliently happening. Yeah, so I'm going back to the.
Sorry if I missed it, but what phase? This is phase at what frequency then?
Phase at what frequency?
We were trying to work that out the other day, weren't we? But I think Claire,
Well, you and me.
You and I?
Oh, no, sorry. Me
You,
and
you and initial. Okay, fine.
And I think Claire, you're saying to do this Hilbert transform, you don't need to choose a frequency, right?
No, but I think they did it out of the weak Mayer waves. So the stuff that's oscillating roughly at Ishil, you said
0.1.
So like, you know, like over a 10-second cycle, or like 5 to 10 second cycles, you have ups and downs in the heart rate, and then you're extracting the phase out of this slow moving signal. So are you in the exhaling or like inhaling stage of the process? I think is what it means.
But that's like the theoretical reason to do it, but you don't actually choose frequency.
Yeah,
it's
exactly.
just whether it was going up or whether it was going down.
So you can see here the Mayo wave is like roughly centered around 0, and then they divide this from the mean to the max. Like the max would be 0 angle, and
Yeah.
the minimum would be 180, and then it rotates like this. So when they go around the respiration circle, they go around the polar float. Yeah.
So it's almost like taking the derivative of the wave, right? We can say that, I think. Like a slope. What's happening to the slope?
I wouldn't say this, but I'm smoking. Not really.
Okay.
So where are you in the cycle more than the derivative? Yeah.
But the cycle itself actually like how they define it is basically whether it's increasing or not, rising or declining, right?
Yep.
Yeah.
But the reason we were also discussing it is like whether we could look at this, but kind of concluded that you would need, this only really makes sense if the infant is kind of sitting quite still, not really doing anything else, and then maybe you've got a very steady heart rate, and it makes sense to look at these local peaks and troughs. But in our data, I'm not sure such an analysis would be possible or make much sense, because any increases or decreases in heart rate are more about general arousal level rather than these oscillations that they're talking about.
Well, no, you would expect them to be tightly associated. I can't remember. I've done Fourier decompositions, I'm sure, in a heart rate data at up to 0.1 hertz, and I've never seen this jump out that you get this like more activity at this range, more periodic activity at this range than you get at other ranges. Which might be because of the points you raised.
Yeah. So I'm continuing then. Yeah. So and then this is a different analysis that they made. They wanted to understand how heart rate and breathing rate work together around the time an animal makes a sound. So they made a plot which is called the state space plot, where each point shows combination of heart rate and breathing rate during a vocalization. So this is the one I just described when I talked about the covariance matrix. So for each moment or for each vocalization, they computed the median heart rate and respiratory rate, and then they plotted these together in a 2D graph, which you see here, heart rate on one axis and respiration on the other. And then they tracked how heart rate versus breathing rate changed over time from 25 seconds before a call to 20 seconds after. So in this graph, you see actually the green plus sign is the start of the call. I'm sorry, 25 seconds before the call. And then it continues along the line. It goes out of the green shaded area and then comes back to it until the 20 seconds after the onset, which is depicted with the red plus sign. So each point in the plot shows what the heart rate and breathing were doing, what's happening in those two at a specific moment in that window. So it's like we're moving across time along the line you can see here. So each point in that plot represents a moment in time. And it's heart and respiration pair. So every point corresponds to a pair of heart rate and respiration. So to understand how much variation there was in heart rate and breathing, overall, they used a reshuffled version of the data. So what they did is they assume that they have the covariance matrix consisting of pairs of heart rate and vocalizations at each point, and they shuffled the data so much randomly so many times, which is called bootstrapping, to generate the null distribution. So, and this null distribution is what you would expect by chance. And so they fit a multivariate Gaussian distribution, which is this one I'm doing right now, to see the cloud of all possible points. And then they took the middle of this bell-shaped curve, all the data points, and they created this cloud, which you can see in the green shaded area. They put that into the graph there. So this shows where values are most common and where they are rare, which is along the edges of the contours. So this is like a topographic map. So they show how dense and variable the data is. So that green shaded region represents 95% 95% confidence interval. Yeah. So this null model area, green area, is what you would expect by chance if there was no specific relationship between heart rate and respiration during vocalization, basically. And then next, they found that cardiorespiratory activity oscillates at the edge of the 95% region of the state space. And 23 seconds before the call, the activity leaves the baseline region as heart rate increases, followed by a quick drop in respiratory rate 2 seconds before the call onset. So if you look closely to the blue line at the very bottom of the line, there's a blue area which you can see between little arrows. That is when the call is happening. So a call happens when it's outside of the null hypothesis area. Yeah. So this is like an attractor state. So an attractor is a stable pattern the system tends to return to. So in this case, this is like a default arousal state, this green area. And then a vocalization doesn't just happen randomly. It emerges when the body's internal state departs from the baseline. And then the body's internal rhythm helps trigger vocalizations. Yeah. So it's like a physiological event impacting the whole system. Yeah. So
that it seems weird that they did that without controlling for the fact that heart rate and respiration rate are related, what we were talking about earlier.
yeah, they took the both as a combination data, combination unit of, yeah.
Oh, I see. So go back to how you did the bootstrapping. Sorry, how they did the bootstrapping.
So every point in this graph is a combination of, like, every point is a moment, like on the graph. If you choose.
Yeah, but the baseline, because you said at one point the baseline, that shaded area, is assuming that the heart rate and respiration rate are completely independent of each other. Yeah.
Yes.
But where you had on your slides how they described the baseline, how they did the bootstrapping. So your next slide.
No. I can try to. Sorry.
Maybe I just read we consider this baseline as an attractor.
So this is okay. So what I'm getting is don't look at the lines on the graph, but just look at the green shaded area. That is not real data.
Yeah, no, I get that. That's the bootstrap.
Yeah.
Yeah. But did they do the bootstrapping whilst preserving the fact that whenever heart rate goes up, respiration, whenever respiration rate goes down, heart rate will go down? Yeah. There's a strong relationship between respiration rate and heart rate.
I don't have an answer to that question. Sorry.
Okay. Yeah, and then the other thing, the weird thing is they've already shown all these other different relationships. So, you know, are these relationships that they're showing between arousal and vocalizations, are they the same as the previous ones they showed or not? That's what, or are they completely independent would be my other question.
Yeah. Like, you mean the two papers, across two papers that they have?
No, even, oh yeah, sorry, this is the PNAS paper, yeah. Is this the PNAS paper now?
No, this was, I went
back to the
2016. This is the PNAS paper. This one.
Yeah, but you went back after that to the 2016.
Yeah, so this is, I just wanted to mention this.
That was just one slide on that, yeah.
Yeah, this is a very short paper also.
Yeah, I mean, if we got a bit of time, should we do a bit of big picture? So for people who are thinking, why the hell do we care about this? Do you want to say a little bit about why the hell we care about this issue?
Why do we care about this? We care about this because we want to look at how arousal is related to the production of vocalizations, and how it so in the actually at the very end of this paper they talk about how future decoupling of arousal and vocalization needs to be examined, which Gio is doing in his paper. So this is basically looking at, in my opinion, how arousal and vocalization are coupled together and what happens. So this is basically showing that they are linked. There's a link between those two. But then in Gio's paper, he found that across development, this link gets decoupled as infants become more mature towards the second year of life. And in my case, I want to do research in psychopathology, so I what happens to this coupling and then possible decoupling, and if there's a difference in that account, like if I'm hypothesizing that maybe infants with autism have difficulty with coupling in the first place, like they may not be using this vocalization as a form of entering themselves into parasympathetic states as a way of self-soothing, maybe. Like there's a, yeah, the basic idea is that for decoupling to happen, there needs to be fundamentally a coupling that have occurred before. So we want to look at those relationships as well.
Yeah, good. And Gio, do you want to say anything on the decoupling thing or not?
Yeah, I suppose so that this group with the marmosets had looked at how this relationship between arousal and vocalization changes with when the marmosets are getting contingent feedback from their caregivers. So they found that the more feedback that they were getting, the less of a relationship they had between, the less predictive arousal was of vocalizing. So that's, yeah, also something that we're interested in looking at. So, and I guess that the theory being that at first things are really driven by arousal, and there's no, obviously, like, you know, very young infants, there's not necessarily like a communicative intention behind their vocalizations, but the more that vocalizations, which may initially be quite just reflexive and arousal driven, do get responded to as if they are intentional. Is this drive, is this like kind of what the foundations of later intentional speech are built on? And then when you get lots of, you know, you get response, and then you start actually, you get that reinforcement from your caregivers, then the infants are more likely to vocalize again. And then this is not an arousal driven vocalization, that's a vocalization that's driven by the fact that I'm now in an exchange with the people around me.
Yeah. But I'm guessing this exchange is not completely like alternative, but I think there's some level of arousal which still stays coupled to some extent. And the reason why I said this is because this paper was published when the infants were 24-month old. So there's still some remaining coupling, although not so much as those that happened in previous months. But there's still, like, if they have these outputs, then that is also an indication of some form of link between arousal and vocalization, but maybe not so strong as before.
Well, also maybe it depends on the type of vocalization that's being made.
Yes, because they say like the recognizability of a vocalization, they interpret it as To what extent does this vocalization sound as a word? So it's even like somewhere between canonical bubbling to actual word production. So I think that's interesting to look at.
And 90 to 150, that is at a trough. That's it. So vocalization is more recognizable as a word when the heart rate is at a low.
When it's declining.
Yeah. And we did, like, when I've looked at our coding, the heart rate of canonical syllables is lower than that of other categories. So that fits with this.
That makes sense then.
Yeah.
Mhm.
Juvenile, I just had one question. Do we know for adults, like for whispers, like I presume you do need to have some increase in arousal for doing any action. So do we know for adults that there are instances where there is no increase in arousal at all before a vocalization? Like for example, in whispers or something like that, or would you assume that, or
No, no, for adults. So
Yeah.
I did a paper a couple of years ago that for adults, there's no this pattern that the heart rate increases gradually before vocalization, decreases after. It's completely gone by adulthood. And then Gio's just doing a paper showing it kind of gradually become decouples. So it's definitely not, it's only there in infancy, we think. I mean, we now got good evidence, so it's only there in infancy.
But did you see that in her comment on my paper, Sam, on that point that you just made, Anne Waterman was looking at your plot and she thought that it's not completely gone.
Oh, really?
But maybe it's just worth me looking at that in our data.
Yeah, for sure, yeah. Yeah, fair enough. But then this is just for those coming from, this is from coming at language development from a very different perspective to, you know, the hard nativists that people would have learned about as an undergraduate. So, you know, there used to be a big movement that kind of language and symbolic communication is hardwired into our genes. Yeah. And this is very much the kind of hard opposite end. This type of research is the hard opposite theoretical end, which is, you know, we basically do stuff reflexively at random. Yeah. Like that. And then some of that elicits a response. And then we start doing that in order to elicit a response independent of our arousal state. So it's a very different theoretical approach to the approaches to studying language that are popular, you know, 20 years ago. And obviously, you know, it's not a question that either one's right or the other's right. It's all kind of probably a bit of both, but yeah. Anyway, round of applause, Rachel. Very nice. Very clear presentation. Well done. Any more final comments? No.
Oh,
Yeah.
just say I went to a talk on the general motor movements that infants make at 5 months today. Did it also undirected and kind of explore all the planes of motion, and it kind of reminded me of that a little bit. Maybe we could talk about it.
What? Okay.
Oh, not us
I see.
generally. Sorry, me and Ishil.
Yeah,
Okay.
yeah, sure.
Not going to talk about it to me. Okay, not you.
Well, we can talk about it too, Sam. I'm sorry.
Fine.
Obviously.
To me. All right. Yeah. Okay. Good. Well done, Ishil.
Thank you.
Bye.